Research on various time forecasting algorithms for predicting COVID-19 cases. K. Rajeswari, Department of Computer Engineering, Pimpri Chinchwad College of Engineering, Pune, India. Tejas Podutwar, Department of Computer Engineering, Pimpri Chinchwad College of Engineering, Pune, India. Sr. Vispute, Department of Computer Engineering, Pimpri Chinchwad College of Engineering, Pune, India. Akash, Mandana, Department of Computer Engineering, Pimpri Chinchwad College of Engineering, Pune, India. Vighnesh, Pathrikar, Department of Computer Engineering, Pimpri Chinchwad College of Engineering, Pune, India. Akshay, Siddannavar, Department of Computer Engineering, Pimpri Chinchwad College of Engineering, Pune, India. Abstract: The World Health Organization declared the COVID-19 outbreak a public health emergency of international concern on January 30, 2020, and a pandemic on March 11, 2020. Now, 1 year after the outbreak of COVID-19, the virus has taken up new mutations and is becoming increasingly harder to predict in matters of its behavior as well as severity. In this study, various approaches for time series forecasting for coronavirus, COVID-19, cases have been compared. Statistical methods, i.e., linear regression, susceptible infectious recovered, SIR, autoregressive integrated moving average, Arima, generalized autoregressive conditional heteroscedasticity, GARCH, threshold GARCH, TGARCH, exponential GARCH, EGARCH, and seasonal autoregressive integrated moving average, SARIMA, have been compared to deep learning method, long short-term memory, LSTM, using various performance parameters. Based on the predictions and forecasts of the better algorithm, healthcare workers could take proper decisions at the right time in providing kits to health centers and other aids to the population. As per our observations, as the number of days of forecast goes on increasing, the error rate of the model also increases. Forecasted trends also show that on average for fewer days, statistical methods tend to be better, whereas, for forecasts of greater days, deep learning methods tend to be better. Keywords: COVID-19, deep learning, statistical modeling, time series forecast. Introduction. In late December of 2019, many health centers reported a bunch of patients with pneumonia of unknown cause. All the patients were linked to a seafood and wet animal wholesale market in Wuhan, China. 9. The World Health Organization, WHO, then announced coronavirus, COVID-19, the virus responsible for the current pandemic. Currently, many countries are still struggling while some have controlled it to some extent with vaccination and preventive measures. 8, 10, 14. Now, 1 year after the outbreak of COVID-19, the virus has taken up new mutations and is becoming increasingly harder to predict in matters of its behavior as well as severity. In this survey, time series models are compared to foretell the epidemiological trends of the COVID-19 pandemic. Based on the predictions and forecasts of the better algorithm, healthcare workers could take proper decisions at the right time in providing kits to health centers and other aids to the population. Present results give insights on the algorithms which are better than their counterparts at predicting the surge in cases, thus highlighting the importance of social distancing and implementation of preventive measures of COVID-19. 2. Literature survey. Autoregressive integrated moving average, Arima, and seasonal autoregressive integrated moving average, SARIMA, are frequently used prediction models for univariate time series data forecasting. Initially, the data is collected and converted to stationary data using differencing. Then, using autocorrelation function, ACF, and partial autocorrelation function, PACF, the parameters for the Arima and SARIMA model are determined. Using the kernel density estimate plot, KDE, and quantile, Q, plot, the errors are realized. A sample plot is created, which is compared to the test data. After adjusting for errors, a forecast is made. 1. K. Arun Kumar et.al. used Arima and SARIMA, statistical models, to develop a 60-day prediction of collective COVID-19 cases for top 16 nations, in which the Arima model proves to be more accurate. They concluded that 9 countries showed an exponential increase in confirmed cases. 10 countries have shown exponential growth in the number of deceased people. And in 3 countries, the projections were stable. 1. Kinsey used a modified version of Arima, which incorporates the generalized autoregressive conditional heteroscedasticity algorithm, GARCH, which is better for data containing volatility clustering, i.e., great changes tend to be followed by great changes, of either sign, and minor changes tend to be followed by minor changes. 6. Kinsey used 1 year's data to model 1 day ahead forecast of the days following the first wave, second wave, and third wave, in which autoregressive moving average, generalized. Autoregressive conditional heteroscedasticity algorithm, Arima GARCH, had the lowest RMSE on average, whereas Arima, threshold GARCH, Arima TGARCH, and Arima, exponential GARCH, Arima EGARCH, had mixed results. These models proved better when comparing sudden increases or decreases in the number of COVID-19 cases. 3. Deep learning has a significant contribution to the field of machine learning. Different time series forecasting algorithms like the traditional recurrent neural networks, long short-term memory, gated recurrent unit, fall under the category of deep learning, which can be used for the forecasting of future COVID-19 cases. Vinaykumar Reddy Chimmula, Lejong 12 had presented a model for the time series forecasting of COVID-19 cases in Canada with the help of deep learning, where long short-term memory LSTM was used to predict the real-time transmission of the new cases. The data for the research was taken from the dataset provided by Johns Hopkins University, JHU, and the Canadian Health Authority. The dataset consisted of data of confirmed cases till the 31st of March 2020. The suggested model had no assumptions, unlike the statistical and machine learning models. Mean square error was used as the evaluation metrics. The results of the study were able to predict a certain exponential increase in the confirmed cases of COVID-19 for the coming months in Canada. The research done by Nushin IOB ETAL15 consisted of 3 different methods, i.e. LSTM, convolutional LSTM, and GRU, to forecast the new cases as well as the new deaths cases for the countries of Australia and Iran. The novel approach used the above-mentioned 3 models with their bidirectional extension, which was done for the first time to determine the forecast of the new and the death cases. The neural networks of these models consisted of an input layer, output layer, and 3 hidden layers. The activation function used to catch the nonlinearities in the data was the rectified linear unit, ReLU. The forecast was done for the next 1, 3, and 7 days. The results showed that the bidirectional extensions of these models proved to be better than the vanilla models. Regression analysis is a forecasting model that estimates the relationship between 2 or more variables. 3. It is amongst the most commonly used machine learning techniques for forecasting purposes. Linear regression is a commonly used type of predictive analysis for. The overall idea is to find the dependency of one variable over the other using a best-fitting linear equation. For using the linear regression model, sklearn.linear_models package is imported from the library in Python 5. Simple linear regression and multiple linear regression analysis help in understanding the various epidemic data points of India and the relationship between them. It is considered to be amongst the most significant predictive models. Limitations of the model can be due to the use of fewer independent variables or information and inaccuracy in the number of contact tracing cases. If the number of contact tracing cases is decreased, it will indirectly decrease the number of daily active cases. 10. The Susceptible Infectious Recovered, SIR, model belongs to basic epidemiological models which are considerably foretelling for diseases that are transmitted from person to person. 2. Mohammed N. Ali Nazi, Fawaz S. Alanzi, Hanin Al Abdul Razak 7 have used a time-dependent SIR model that predicts infection rates as well as recovery rates for Kuwait. They experimentally studied the legitimacy of different R0 values over a time duration of 94 days and found that the SIR model is most accurate for R0 values in a range of 3 to 4. Pavel Sharir et.al4 have used the susceptible, exposed, quarantine, infected, recovered, death, SECIRP model, which is an altered version of the SIR model 11.19. The sensitivity of R0 to parameters has been studied. Sensitivity analysis demonstrates which parameter is more dominating for the system. Simulation is done using 4th order RK, Runge-Kutta, by the medium of MATLAB for the rate of susceptibility, infection, recovery, and also for graphs of number of dead people vs date, number of infected people vs date for better understanding of the behavior of COVID-19. 4. Weston C. Rhoda et al. 18 have demonstrated that the SIR model is considerably more accurate than the SEIR model for the outbreak of COVID-19 in Wuhan. They show that more intricate models need not be more accurate. The dataset used by most of the researchers in their study was taken from JHU, which is updated every single day. The general procedure for using this raw data for the prediction was illustrated. First, some pre-processing is done on the raw data where the data is converted into the time series data, which is then divided into the testing and training set. The training data is then fit into the different models which are evaluated using the evaluation parameters like RMSE, MAE, REMSL, and MAPE, etc. Then the model is adjusted by looking at these performance parameters. Once training is done, the model is tested with the testing dataset and then the appropriate model is chosen for forecasting. Here, as the number of days of forecast goes on increasing, the error rate of the model is also increasing. I methodology. A linear regression. Simple linear regression analysis is a technique to find the relation between two variables. One of the variables is an independent variable while the other one is dependent and changes with the change in the independent variable. General representation of linear regression is given by y equals b0 plus b1x plus e1. The only limitation of using linear regression is that it often uses the mean value of both input and output variables to define a relation between them. Just as the mean can't fully describe a single variable, the linear regression model is just not a reliable method for predicting variable relationships. Therefore, the various factors which hindered the use of SLR are addressed with the help of the multiple linear regression, MLR, model. While in simple linear regression, only one independent variable is involved, multiple linear regression uses two or more independent variables and one dependent variable to estimate the relationship between them. General representation of multiple linear regression is given by y equals b0 plus b1x1 plus bnxn plus e2, where y equals the predicted or expected value of the dependent variable. b0 equals value of y when all dependent variables are equal to 0. b1x1 equals the regression coefficient, b1, of the first independent variable, x1. bnxn equals the regression coefficient of the last independent variable. E equals model error, variation in our estimate of y, 21. Initially, the dataset is cleaned by removing any missing and unwanted values. This process is called data cleaning. After the dataset is completely ready, it is split into two parts: train and test dataset, mostly 80% for training and 20% for testing. The model is first trained using train data and test data to verify that the model fits the data well. Then the fitted regression equation with future dates is used for prediction for Arima. As opposed to classical regression, the main notion behind time series forecasting is that the measure of some variable at a certain period will depend on the measure of the same variable at previous period 17. Arima is a byproduct of combining differencing with autoregressive and moving average models. The predictors include the lagged values as well as the lagged errors for the data. Arima model is expressed in terms of Arima, P, D, Q, where P is the order of the autoregressive section. D is the degree of first differencing. Q is the order of the moving average section 16. Thus, the following representation of Arima is used for predicting daily COVID-19 cases. Where YT is the number of cases for the TTH day, ET is the error between YT and the actual value for the TTH day, and P and Q are the parameters used for Arima, where P is calculated by considering the partially correlated values with YT and Q is calculated by considering the correlated values with YT1. See SARIMA. Seasonal Arima, SARIMA, is formed by including further seasonal parameters, P, D, Q, M, where M is the number of observations per year, to the Arima model. The seasonal model contains both terms, from non-seasonal Arima, as well as the backshift of the seasonal period. The general representation is given by where YT is non-stationary Arima, WT is the Gaussian white noise, B, is the non-seasonal autoregressive component, B, is the non-seasonal moving average component, D is the seasonal differencing, FP, BM, is the seasonal autoregressive component, and TQ, BM, is the seasonal moving average polynomial. B is the backshift operator where BKYT equals YTK, 5. The expressions for the non-seasonal autoregressive, moving average, seasonal terms for seasonal AR and seasonal MA model are 1. Fig 2. One general process followed for developing Arima and SARIMA models. GARCH. The central assumption behind the ARMA model is that the data is stationary, hence the expected variance of all terms at a given point should be the same. This assumption is called homoscedasticity and it is an improbable assumption. To overcome this as well as volatility clustering, Engel 3 introduced the autoregressive conditional heteroscedasticity, ARCH, model as a new type of stochastic process. The general GARCH, 1, model is given by the mean equation presented in 11, known as the conditional variance equation. S2QT displays one value in advance forecast variance built on past information. Conditional variance of the rate of growth for new cases for a particular country Q, S2QT, is a constant function, the ARCH term, E2QT1, and the GARCH term, S2QT1. ARCH term is the previous data's consequence, measured as the interval of the squared error terms from the mean equation. The GARCH term specifies extended term volatility, measured as last data's forecast variance. D. Sir. It is a mathematical model belonging to basic epidemiological models which are considerably foretelling for diseases that are transmitted from person to person too. It is a compartmental model in which total population, N, is divided into S, the number of susceptible individuals, I, the number of infectious individuals, R, the number of removed, and immune, or deceased individuals. To represent the number of individuals in one compartment at a time T. S, T the number of susceptible individuals. I, T the number of infectious individuals. R, T the number of removed, and immune, or deceased individuals. Assumptions. We need to make assumptions to simplify real-world situations into mathematical 19. 1. Total population, sum of all compartments remains constant. 2. Birth rate and death rate are assumed to be negligible. 3. Everyone is susceptible. 4. Rate of infections is directly proportional to contacts. 5. Infectives recover/die at a constant rate. Mathematical representation. Prior assumptions can be represented in form of mathematical equations. Equation 12 depicts the first assumption I.E, total population, sum of all compartments remains constant. 19. Initial conditions, at time t equals 0. Equation 14 shows the initial amount of susceptible people represented by term S0, at the start almost everyone will be susceptible. Equation 15 shows the initial number of infectious people represented by I0. Initially, it is going to be some very small number of people, maybe just one person. Equation 16 shows that no people recovered initially. We use a system of differential equations to represent the rate of change in each compartment. Equation 17 shows the rate of change of susceptibles concerning time, where A represents transmission rate, S is the number of susceptible people at that time t, and I is the number of infectious people at a time t19. Thus the contacts between susceptibles and infectious are represented by S times I. The sign is negative since people are leaving the susceptible compartment 19. Equation 18 shows the rate of change of infectious disease with respect to time, where B represents the recovery rate. In 18, it is shown that A, S times I, people are added to the infectious compartment and by people are removed from the infectious compartment 19. Equation 19 shows rate of change of recovered where B represents recovery rate and I is the number of infectious people at a time t19. Fig. 3. 20 compartments in the SIR model and transition rates between them. The spread of disease depends on the rate of change of the infectious compartment, which is represented by equation 18. If the value of d/dt is greater than 0, we can say the quantity of infectious individuals is increasing and we are moving towards an epidemic. Otherwise, we can say the quantity of infectious individuals is decreasing and we are moving away from an epidemic. New people are being infected but they are recovering faster. If the value of 20 is greater than 0, then 21 represents the situation when the value of 18 would be greater than 0 near time t equals 0. 22 is obtained by moving by 0 to RHS. 23 is obtained by dividing both sides by I0. 24 is obtained by dividing both sides by B. Thus from 24, we can conclude that spread of the disease depends on the value of the term S0/B. If S0/B is greater than 1, then the disease is moving towards an epidemic, and if its value is less than 1, then the disease isn't moving towards an epidemic. Reproduction number. This term S0/B from 24 is called basic reproduction number, represented by the symbol R0. It conveys the average number of secondary infections an infectious person will cause while he/she is infected. Here the term A/B is termed as contact ratio, symbol Q. It represents the fraction of the population that comes into contact with an infected individual during a period when they are infected. Thus, R equals Q times S0, 25. 25 represents the basic reproduction number in terms of contact ratio and the number of susceptible people around time t equals 0. Deep learning. The dataset where every data point is collected at periodic intervals of time is called the time series data 12. So, Covid-19 data can be termed as the time series data. The future values of the cases depend on the trends in the past. So, various mathematical and statistical methods have been suggested for modeling the time series data. But these models tend to have some limitations when used for modeling the time series data. These models fail to recognize the complex patterns in the time series data, which is very useful for forecasting future values. These models work well for the few-step forecasts but not in the long-term forecasts. The missing values in the dataset affect their performance. So, to overcome these barriers of the statistical methods, deep learning models came into the picture to model the complex patterns in the time series data efficiently. The following section covers different deep learning models like feed-forward neural networks, RNN, and LSTM to be used for time series forecasting of the COVID-19 cases. A. Feed-forward neural network. Multilayer perceptron is a type of feed-forward fully connected neural network consisting of layers of neurons. A neuron in these neural networks is a node that accepts some data as an input and performs some mathematical operation on it and then produces some output. The COVID-19 dataset is time series data, so this cannot be directly fed into the network as an input. So, some pre-processing needs to be done. The dataset is first converted into a regression dataset and then it is fed into the multilayer perceptron, MLP, for training purposes. 27. A feed-forward neural network consists of different layers, among which the first one is the input layer, the second set of layers consists of the hidden layers and the last layer is the output layer, can be termed as a multilayer perceptron. 25. The MLP consists of at least 3 layers where the number of hidden layers will be 1 or more. Each neuron in a particular layer has some inputs where each input will be associated with a particular weight. Then the weighted sum of all the inputs is computed by the neuron, which is then passed to an activation function. The data that we use in real-life examples are seldom going to be linear. So, most of the data that we deal with have nonlinearities in them, and to handle and analyze these nonlinearities an activation function is used by the neuron. The different types of activation functions that are used can be sigmoid, 10 or ReLU. The weights associated with each input for a particular neuron are initialized with some random values. When the data is fed into the neural network, it is propagated into the forward direction and the output is produced. 24. The error produced in the output is called the loss function. During the training process of the neural network, this loss function is minimized by adjusting the weights associated with the inputs and a better prediction is made. Y equals G, W0 plus, equals 0 ZW, 26. Here, Y. Output vector. WO equals bias. ZW equals linear combination of inputs. G equals nonlinear activation function. The linear combination of the weights and inputs ZW, is added with a bias value, WO. This weighted sum is then passed to a nonlinear activation function, G, which gives the output for the perceptron. B, RNN. RNN are special types of neural networks which are used to handle and analyze the sequential time series data. It is a type of neural network where the output at the particular time step is not only dependent on the inputs given to the network but also on the output of the previous time step. 26. This is an evolution of the previous feed-forward neural network discussed. The time series nature of the COVID-19 data has patterns in the past that need to be stored in a memory to generate better future predictions. This is where the RNNs perform better than the feed-forward networks, where there is no relation of the output produced at a particular time step with the output produced at the previous time steps. So, the RNNs are said to have a memory where these outputs of the previous time steps are stored for future predictions. 29. So, the RNNs tends to perform better than the feed-forward neural networks in the time series forecasting of future values. RNNs suffer from the problem of vanishing gradients, which leads to the incapability of the network to capture the long-term dependencies. 28. So, to tackle these limitations, some modified models of the RNN were developed. In RNNs, the hidden cell state, HT, is dependent on the present inputs, XT, as well as the previous cell state, HT1. C. LSTM. LSTM is the modified version made from the RNN, which eliminates the problem of the long-term dependencies of the traditional RNNs. The output of each cell of the LSTM is passed to the cell at the next time step. The process is continued until we reach the final LSTM cell and generate the output. The design of the LSTM cells was made to tackle the problem of vanishing gradient by storing the information in the memory cell for a longer duration of time. The architecture of LSTM is built with a cell state and 3 different gates, each of which is used for handling different purposes. 15. Each LSTM block consists of 3 different gates, which are forget gate, input gate, and output gate. The forget gate is fed with the information from the previous hidden state and the current input. These are then passed to the sigmoid activation function. If the value comes out to be closer to 0, then the gate discards this information, and if it comes out to be near to 1, then it preserves the information. So, this helps the LSTM block to remove irrelevant information. The input gate helps to update the cell state of the LSTM block. This gate consists of two different activation functions, among which the first is the sigmoid function, which performs the same function as the forget gate, and the second is the tan-i.e10 hyperbolic activation function to squish the values between -1 to 1, which helps the network work on the data uniformly. Then the sigmoid output is multiplied with the tan output, and then the cell state is updated accordingly. The output state will decide what information needs to be passed to the next cell as the previous cell state. In this way, the architecture of the LSTM helps eliminate the problem of long-term dependency. For implementation. Introduction. In this section, we decided to compare and contrast different models on the same data set, JHU daily cases for India 30, by fixing the prediction period, and also by predicting for different time periods starting from October 25th, 1 day, 7 days, and 1 month, up to November 25th. In this section, the procedure followed for time series forecasting of daily COVID-19 cases is discussed. Initially, the raw data consisting of cumulative values for COVID-19 cases were collected from the JHU dataset. In time series forecasting, we require the past data of daily COVID-19 cases in order to forecast the future values, hence these values are collected from the dataset, and before using the data for training, some pre-processing is applied. In the pre-processing part, the data collected from the dataset consisted of the cumulative values of the COVID-19 cases, so the first step was to convert these cumulative values into daily values. The dataset consisted of some negative and zero values which were removed. Fig. 5 depicts the daily COVID-19 cases in India as per JHU dataset. B. Linear regression. On training the linear regression model with an 80 days dataset, a straight line with a negative slope is formed. The regression line can be seen coinciding with the actual cases trend line at a few points and then gradually moving away from it as the actual cases tend to rise, hence indicating a potential reversal. Thus, showing that linear regression works better on a linear dataset. Fig. 6 depicts linear regression predicted vs actual trend lines from October 25, 2021 to November 25, 2021. The root mean square error is calculated for 1 day, 1 week, and 1 month. The 1-day RMSE is 2.52 times 10 cubed, 7-day RMSE is 1.45 times 10 cubed, and the 1-month RMSE is 2.76 times 10 cubed. See Arima. On processing the initial data and checking for stationarity, by performing an augmented Dickey-Fuller test, the data came out non-stationary. Hence, by using first-order differencing, we got the following ACF and PACF plots. Fig. 7 depicts an Arima 2, 1, 2 model. After training Arima 2, 1, 2 on the recent subset of cases, from June, we got Fig. 8. Fig. 8 depicts Arima 2, 1, 2 predictions from October 25, 2021 to November 25, 2021 with a 1-day RMSE of 2.53 times 10 cubed, 7-day RMSE of 2.47 times 10 cubed, and a 1-month RMSE of 4.32 times 10 cubed. SARIMA. For SARIMA, we tried a brute force approach to determine the parameters in a stepwise manner, by using a period of 3 months and minimizing AIC. This resulted in a SARIMA 2,1,2, 2, 0, 1, 3, with an AIC score of 2.36 times 10 cubed. After training. Fig. 9 depicts SARIMA 2,1,2, 2, 0, 1, 3, predictions from October 25, 2021 to November 25, 2021 with a 1-day RMSE of 1.58 times 10 cubed, 7-day RMSE of 1.48 times 10 cubed, and a 1-month RMSE of 2.46 times 10 cubed. LSTM. After the general pre-processing of data, we get the daily COVID-19 cases of the past data. Then some additional pre-processing was done on the dataset, which includes the scaling of the values of cases in the range of 0 to 1. LSTM is sensitive to values of the data used for training, hence the data needs to be scaled. The data used for training the model consisted of the daily COVID-19 cases from 9th of April 2020 till 24th of October 2021, which consists of the data of a total of 563 days. In order to feed the data into the LSTM model, we have to create sequences of the values from which the model produces the output. Before training the model, we need to define the configuration of the model, which consists of determining the number of layers and the number of units in each layer. So in this study, we have used the LSTM model with a total of 3 layers and 1 output layer, where the first layer consists of 150 units, the second and the third layer consists of 64 units, and the output layer consists of 1 unit, which corresponds to the value predicted by the model. Then the model was fit with the sequences of the data and was used for prediction of the future cases. Fig 10 shows the prediction of COVID-19 cases using LSTM from 25th of October 2021 to November 25, 2021. These predictions show the RMSE of 1.95 times 10 cubed for 1 day prediction, 1.48 times 10 cubed for 7 days prediction, and 1.41 times 10 cubed for 1 month prediction. Conclusion. After having reviewed the related literature, we came across the following limitations. First, the time frame of the dataset used for the study and the predictions for the same don't align. Second, the forecasting range of the chosen literature varies, thus making it hard to conclude. Also, linear regression doesn't work optimally for nonlinear data. The SIR model becomes inaccurate for long periods as one or more of the assumptions are violated. In this survey, the results of various statistical and deep learning methods for predicting COVID-19 cases are compared. All of these included data extractions, data pre-processing, data visualization, prediction using machine learning algorithms, and error checking. As per our observations, as the number of days of forecast goes on increasing, the error rate of all the models also increases. As conventional knowledge states that, deep learning models tend to outperform statistical models in the long term. Our observations aligned with this statement. For forecasts of fewer days, statistical methods, SARIMA for 1 day and linear regression for 7 days, were better on average, whereas, for forecasts of greater days, deep learning method, LSTM for 1 month, tend to be more consistent.